So we're going to shift gears. We've got Claudia up next, who's just going to plug in. So Alex talked a lot about hypothetical red teaming, obviously. Most of us use Electron apps now. We might realise that, we might not, whether it's Slack or any one of half a dozen applications that we all have installed. Claudia is going to talk to us today about the blue team side of looking at Electron apps and the forensics piece. So while Claudia gets plugged in and gets her slides set up, could you please give her a really big round of applause and make her feel welcome? Thanks, Claudia.
Good morning, everyone. So nice to see you all bright-eyed and bushy-tailed this morning for my presentation. Thank you for coming to my talk, Electron Apps Unplugged, Unveiling Digital Forensic Treasures this morning. This is my first time ever at any cyber conference, so I don't know why I decided my first time should be on stage, but here we are. Before we start, I would like to acknowledge the traditional owners of the land on which we meet today and pay my respects to elders past, present and emerging. And I would also like to comment that from here on out, it's about to get really pink. So if you want to leave now, I won't be offended. For those of you who don't know me, my name is Claudia. I'm an investigator at CyberCX within the Digital Forensic and Incident Response team, and have been for the past year. My background is mainly system administration and cloud engineering, and I've been in the industry for around 6 years. Some fun facts about me: I got into this industry because I watched Mr. Robot one time at the age of 15 and thought it was really cool, and I've been in the industry ever since. I also like to lift heavy things while I'm not doing nerd stuff, and I also really like pink, as you are already aware. So our agenda today. So first, I'll go through an introduction into Electron apps and what they are. I'll then go through why I don't like Electron apps, controversial I know. From there, we'll work through popular Electron apps and the file system layouts, and then we'll move on to our investigation. So a lot of you may be wondering, what is an Electron app, you ask? An Electron app is like a container that lets regular websites or web applications behave like desktop programs. It's based on Chromium, the same open source project that powers the Google Chrome web browser. It's a way to take web technologies like HTML, CSS, and JavaScript and package them into an application that you can run on your computer, just like any other software you install. So you can use websites as if they were desktop apps without actually needing a web browser. And thanks to a backend powered by Node.js, Electron apps also have access to your computer's file and system. Here are some popular Electron apps that many people use day to day: Discord, Slack, Signal, and Teams, rest in peace. So although these applications are all very distinctly different, they all share the same base and structure for storing data. Although they are all similar, they all store data very differently. For instance, Discord stores messages in the cache, whereas Signal uses SQLite databases for messages. So the Electron app file structure. First, we have the file path of the application itself, which is stored in the user's roaming profile. Majority of all Electron apps store data in this same location. The main two data stores used within Electron apps are LevelDB databases and Chrome caches. It's pretty rare to see SQL databases used for Electron apps, although it is definitely possible. So here is the basic file system structure for Electron apps. We first have the Chromium cache. It's in the same format as the cache storage that's used for the Chrome browser. We also have the long-term text-based storage and the single-session text-based storage, which are both LevelDB databases. The LevelDB databases are primarily used for JavaScript objects related to the application itself. Onto our LevelDB databases. They are comprised of multiple files, with the most important being the .log and .ldb, which contain the stored data. The most recent database transactions are added to the .log files, which are easiest to examine as they don't employ compression. These .log files often repeated updates of the same information, which can be made redundant and may include data that was deleted or overwritten in the past. Once a .log file reaches 4 MB in size, data within it is added into multiple LDB files. The other files, like manifest and current in LevelDB folders, contain organizational metadata for the database. The other most common data store for Electron apps is the Chromium-based cache. Each application maintains its own cache, and the same tools used to parse Chromium browser cache files can be used for Electron apps, making it one of the easiest data stores to review for activity. The index file holds a key table that helps find entries in the cache, while the data files store various details, including administrative info, the actual content of requests like HTTP headers and data. These data files are also known as block files because their file format is optimized to store information on fixed size blocks. When the data is bigger than 16 kilobytes, it's no longer stored inside the standard block files. Instead, it's stored in a file that has no special headers and contains only the data we want to save. These are the individual cache files you can see here on the slide. Another not-so-common data store for Electron apps is an SQLite database. SQLite is a serverless, file-based database that stores structured data in tables using SQL. The write-ahead log file is where the changes are first recorded before the changes are written to the database after closing the application. The shared memory file contains only temporary data, and it is only present when SQLite is running in write-ahead log mode. Also, I just want to be extremely clear. We are not parsing level DB databases today. Don't get me wrong, we love her, we value her, but she is staying in the corner where she belongs. It is quite difficult to manually parse level DB. There are only a few tools that are open source that can parse them well, but they are typically focused on only one application, like the old instance of Teams. There is an open source tool, Forensics IM, that serves as an autopsy plugin and a Microsoft Teams parser. This tool works by parsing the .ldb files, which contain the majority of entries for the old Microsoft Teams, but I wouldn't get too excited if I were you because Teams will be moving off of Electron and onto the React framework in less than a week. Very rude, I know. There are also some other great tools. Axiom does have a great inbuilt level DB parser, as well as a tool called CCL Rabbit Hole, although both cost a lot of money, so maybe next year I'll just have to submit another talk and it's part 2. Claudia's finally able to parse level DB databases. On to our scenario. So we now live in a world where sharing quotes from the hit TV show The Office is illegal. I have acquired the image of the device and have been issued to look into the contents of the machine, including its usage of Electron chat clients. So the first Electron app found on the machine was Discord. So to start off our investigation, I first questioned what I wanted out of Discord. Did I want calls? Did I want attachments? Did I want messages? What was it that I wanted to focus on? And realized to start with, I just wanted to solely just focus on messages. So we are first challenged with getting these message files or finding them within the app's data sources. So I decided to parse Discord's Chromium cache, and I used Nersoft's open source tool, Chrome Cache View. It's typically used for parsing users' Chrome browser caches, which stores a load of generic information like what website a user has been visiting and parts of pages like images, as you can see here. But what is pretty cool and handy for my investigation is that having the Chromium-based the Electron apps allows us to parse the same contents as a user's Chromium browser cache, but just for a different application. Here in this example, you can see that each cached item in Discord's Chromium cache is also associated with a URL, some of which are API calls. An API is like a messenger that allows different software applications to talk to each other. Discord uses its API to fetch data from its servers to show you things like messages, user profiles, server information, etc. It stores some of the data locally in your device's cache, so when you open Discord again, it first checks this location. So if we parse the cache folder for the Discord application, it will provide a load of information, including URL shared, linked external applications, think Spotify, Steam, and YouTube, and plenty of other things. But what I wanted for this particular case is message data. So what I was able to do is filter within the tool for messages and find files that resemble that of a message. Doing that, I was presented with a bunch of .json files, which upon opening, I could see were messages inbound and outbound. I was very pleased with this finding, but I needed a way to bulk export all of these messages out so I could sift through them to determine which ones were of use to my investigation. So to export these JSON files out of Chrome Cache View and onto my local machine, I use this command. This command specifies the location of the cache data, passes the domain and application type of the entries we want to extract, and then copies them to an output directory of our choosing, using the same website directory structure we saw utilized in the previous slide. If we change this value to 0, it will dump all the data with no structure. Usually that's how I store my personal information, but in terms of the case, we want to have some organization to our data. After I ran the command, I navigated to the output, and we can see the same directory setup that we originally saw in Chrome Cache View. In these folders are singular JSON files entitled messages. When I opened them, I was able to see some useful data that was going to help me in my investigation. So to the left is the very gross content of the .json file, which I have put into a beautifier tool for your eyes. As you can see, it contains a lot of useful data. The stuff I was interested in the most to catch the activity was the contents, the username of the user, the global name of the user, as well as attachments and timestamps of the messages. So yay, we found some juicy stuff, but now I have this data on my local machine. I'm tasked with needing a way to grab all the JSON message files. But I only want this very specific data, and I also want an easier way to read it, rather than having to put each file into a beautifier and interpret it. So that led to creating a PowerShell script that could do exactly that. This script is able to grab the JSON output filter for the message files in each folder and iterate over each file for data I was interested in and exporting it to CSV. I also sorted it by the channel ID, so the messages would be in correct order and it would be easier to interpret. And from that, I opened the CSV and found very illegal activity. Not only were we able to identify the illegal sharing of quotes, but we were also able to identify attachments as well. As you can see, I was able to navigate to the URL successfully. This is because Discord's Content Delivery Network, also known as the CDN, is still cached publicly online, allowing users to access files and resources quickly from the distributed servers. We also have the timestamp on when the messages were sent, alongside the message's ID and the channel ID. The channel ID is specific to the user, whereas the ID is correlated with the message itself. So ordering that from the smallest to largest, we get the correct order of the messages. So as you can see, we have I am faster than 80% of all snakes. We also have fool me once, strike one, but fool me twice, strike three. And what else do we have there? Oh, I should have burnt this place down when I had the chance, another personal favorite. But wait, there is more. They were also using another application to share these illegal items, which takes us over to Signal. So I investigated this machine and I was able to see the criminals also using Signal. But an issue I ran into was that the SQL database was encrypted. But after some research that didn't take long at all to find out was that the key is stored locally in .json format on each user's machine. The key is stored locally per install and then resides in the Signal directory. It's in plain text and can be used to unlock the database, but only by using SQL Cypher, which is an extension on SQLite. You might also be wondering about Signal for mobile and thinking, but I don't have Signal for desktop, am I safe? The answer is no, never. The application, no matter the platform, stores data via an encrypted SQLite database. But please don't ask me to do this for a mobile right now, because I have absolutely no idea. So for this scenario, if you have the Signal desktop application, all the data from your mobile app will only sync across from the date you first log into the desktop version. Also, I'm aware this key is per install, but I don't trust any of the red teamers in the room. So once I figured this out, I also figured out that the SQLite GUI is not good at all. When you open SQL Cypher GUI, you'll be presented to add a database and a key, but it will bug out and just not let you in. So because of this, we're taking the long way round. Using the WSL terminal, I was able to open the database and use the pragma command to enter the key. We specify the X at the start of the key because we're specifying an exact byte sequence. Once I successfully opened the database, the first thing I did was print a list of all the tables within the database. I was mainly looking for data sources that would assist me in finding messages related to our investigation. So the first three tables that stuck out to me were conversations, messages, and edited messages. At this rate, I didn't know what was in these three tables, but I knew from the naming conventions that it could potentially be useful. There are definitely some other interesting tables to look at further. For instance, calls history would definitely provide good evidence along with attachments. Emojis is also another cool one, just in case some threat actor's main way of communicating is with emojis. But we kept it simple and just stuck to these three. So to kickstart my investigation, I was going to focus on the conversations and messages table to start with before diving into the edited messages. So starting with the messages table, I struck gold. I was able to quickly identify some values of interest, including the ID, the sent at, received at, type, and body values. The other table of interest was conversations, which was honestly quite boring in comparison to the messages table, but one thing it does have above all was a profile name. Signal used to only profile users via mobile numbers, but as of the recent update in version 7, Signal allows you to replace your number with a profile name instead. So this was also pretty important information because knowing the mobile number is great, but what if they've replaced that with a profile name instead? A mobile number or a profile name is going to be terrific in helping me profile the user. So now I have these particular variables in 2 different tables that I deemed important to my investigation, and now I want to put them into a pretty output and be able to see what was being said. So this is where some fun SQL magic happens, which actually isn't that magical, it's quite standard SQL. But I was able to select the data I wanted and then join the conversations table as well to show me all the data I wanted to see in one output. This did produce quite a lot of entries within the terminal though, and it was quite messy. So I wanted to export it to CSV to clean the output up, and I was also able to set the mode and output and rerun my commands, so I got a nicer output. And we got them twice. We found more illegal activity. So at the start, we have the full name of the individual or the group name, then the shortened version, then the timestamps, phone number, ID, the direction, and most importantly, the content. So as you can see here, we have I am Beyonce always. We also have the worst thing about prison was the Dementors. And then we also have another personal favorite, I've learned to talk a lot, so I've learned to tune myself out. And then I wanted to go back and check the edited messages table as we want to gather all the evidence we can on the machine. So I looked inside and saw it didn't contain much at all, but something it did contain that was quite interesting is the column conversation ID, and it got me thinking. When I originally looked at the messages table, it also had the conversation ID column. So if we add up the values, could it potentially reveal the difference between the 2 messages? It seems like it could, right? Or is that just way too straightforward and too good to be true? So from here, I did a quick, simple query that grabbed all the conversation IDs from the edited messages table and displayed them, and I got this bad boy. So that's good. It's been able to pick up that a message with this conversation ID has been edited. So what would happen if I did the same query, but for the messages table? So back to my favorite child, the messages table. I repeated that query search alongside the contents of the messages. And from the output, I was able to see the conversation ID that we found just before. That's great, but now I'm stuck with all of these messages that have the same conversation ID because they're being sent and received by the same recipient. So how am I going to know which one was edited? So now I was a bit stumped. Because the edited messages table doesn't contain any content data, I had to think of a way to basically go back in time to where the old unedited message was stored. So I think I had an idea. I've got it. Let's merge host forensics and application forensics, introducing volume shadow copies. Volume shadow copies is a feature in Windows operating systems that allows you to create snapshots or copies of files and folders on your computer at a particular point in time. These snapshots are called shadow copies because they are like shadows of your files at a specific moment. This service happens at least once per week, but it can be created more frequently dependent on the host and its operations. Shadow Explorer is a tool that allows users to access and recover files from volume shadow copies, providing a convenient way to retrieve lost or modified files without the need for a dedicated backup solution. What I can do here is see when the last volume shadow copy was and see if that SQLite database exists at that point of time, which it does. In an instance where the write-ahead log file is present, it typically means that there's still data within the file that hasn't been written to the main database yet. It is possible to open this file and find data, but this requires flushing of the SQLite database and can take some time. So in this instance, all changes have been written to the main database. So we managed to snag the SQLite database from back in time, and we were able to open it using the same key as before, because like mentioned previously, the key is per install. But that doesn't typically matter anyway, because if the user did have a different instance of the application, we can just go back to the JSON file using the tool we had before and find the application key. So once I entered the database, I repeated the same query I did previously, and I saw a difference in one of the messages. I was able to see that both outputs had a difference, yet shared the same conversation ID between the tables. We have the current message, I shouldn't have said that, whoops, and the older message, which is, I love inside jokes, I'd love to be a part of one someday. So, yay, this is great. We just found more evidence for our investigation, but again, I can't handle the terminal output, and I also want the names again like we had before, plus all the other correlating data that the messages table gave us. So this just led to more SQL. So here, I first set my mode to CSV output. I then selected all the values from all the tables that I wanted, ensuring that if there were any double ups of columns, to specify the table that they belong to. I then joined on our new edited messages table and specified the conversation ID of interest. From here, I also joined on the conversations table like before, so I can get some names of our criminals, and then I sorted it by the sent out date so that our output was in order. And we got them thrice. Honestly, after that, I think I'm reconsidering naming this talk to SQL with Claudia. You can see the first column is the name, then with the sent at and received at timestamps, with the phone number, direction, conversation IDs, and how they match along with the content. But now you might be thinking, Claudia, that's cool and all, but what about the disappearing function within Signal? Or what if I just completely deleted a message? Would this magical volume shadow copy be able to read it? The answer is yes and no. If anything, it might make our lives a little easier. Reason being, this data is represented as a column in the messages table, so rather than it being on its own table like edited messages. This means we can write another query that grabs all of the columns alongside the content of the messages. When we look at the isErase column in our messages table, we are looking at messages that have been deleted. A simple way we can tie it back to the old database is by the ID column. You can see here on the screen that in our current database, we have the ID of the message, the body, and the number 1, which represents true for the isErased column. Now, if we go back to the old database, we can do the same search we'd used before, specifying the ID we found that correlated to a deleted message. If the user had not deleted the message, in the point of time, you will get the data. So what about the disappearing messages function? Well, this is where it gets a bit interesting. With expired messages in our old database, you can see the body, the timer, in our case 5 minutes, and the ID. You would think this would work similarly to the erase messages, right? Just grab the ID and search for it in the old database. Well, you're wrong. I was wrong. In our new database, if you try and search for the ID from the old database, you won't get a result, and vice versa. See, what happens is when a message expires or disappears, not only does the body get removed, but it also obtains a new ID entirely, so it's not traceable. You can see that here on the slide. It's still definitely possible to get the contents of the message and all the details, but it will take a lot more work to put the pieces of the puzzle together. So that's some interesting findings within Electron apps. Thank you all for coming today. I also just wanted to do a quick shout out to my amazing fellow DFIR teammates, Liam, Lee, and Zach. I appreciate you guys a ton, and they've helped me a lot with this talk, so shout out to them as well. Oh, thank you.
Thank you so much. Thank you, Claudia. And for those that don't remember from the start, not only first conference, but first presentation at first conference. So again, one more round of applause for Claudia.